Okay, well, let's look at today in our second and third class. Technically, we're going to review some statistics, and so some of this will be simple, and some of you have seen it, and some of you won't. And as you know, turbulence is really a statistical phenomena, at least in terms of predictability. It's deterministic and chaotic, but generally we do statistics. I mean, the Navier-Stokes equations, from a physics point of view, are technically statistical when you link them with the energy equation anyway. So statistics will be important for predictability. Now, as I mentioned in the last class, we used the approach of Reynolds in 1895, where we express quantities as what? A mean and a fluctuation. And we'll see that through this class when we do work on turbulence modeling. And we need to apply these, and of course the equations that we're focusing are the Navier-Stokes equations, which we mentioned in the last class, and I won't rederive them or reintroduce them because they've probably been derived in many of your fluid dynamics classes. And the whole problem in this field comes from the nonlinearity of the Navier-Stokes equations, right? And that leads to appearances of momentum fluxes which lead to stresses in the flow. And in fact, you can see terms like u partial x and mu partial 2u partial x squared are going to be problematic. And of course, if they were linearized, we could find solutions, and that's why Stokes' name is attached to the Navier-Stokes equations for his pendulum solution. And when we do Reynolds-Averaging on the Navier-Stokes equations, there's going to be these extra terms, which are the Reynolds stresses, which we might get to today if we make good time. And it results in more equations and unknowns, and that's what's known as the closure problem. So I'll just write that's the closure problem. Okay. Now, I included this image, which I stole from a journal article. And I wrote down here, it's actually from an article by CS, which is so famous. It's actually Cebeci-Smith. And they actually created a really famous model called the Cebeci-Smith model, which we'll talk about this semester. And in this little graph here, we have the x-axis being velocity in, say, meters per second. And this is the distance from the wall. So this would actually be like the wall, if you will. And y is the distance from the wall. And what they did is plot 17 profiles, which are actually at the same distance from the plate. And each one of these profiles, they've just taken pictures of hydrogen bubbles at a distance downstream. So these are 17 profiles of bubbles downstream on the plate. Okay. And they just staggered them on the graph. They were really all at the same physical location after a certain amount of time of traveling downstream in a convected, fully turbulent boundary layer. And this whole experimental technique, if you haven't heard of it before, is actually a hydrogen bubble technique. And what they do is have a wire and send electricity through it. And I'm not an expert on this technique at all, but apparently bubbles form and they go down and they track them with a camera and take pictures and just basically correlate them. The time they did these experiments, of course, they had basically a technician draw these lines and make the plot. And you'll notice some funny things about these plots. If you look at them, is there's these little inflection points here. And it's not really writing purple there. And of course, it looks like a multi-valued function. But that doesn't make any sense in a real flow because, of course, at some distance from a wall, you wouldn't have multiple velocities at a particular point. And so by tracking hydrogen bubbles, you get actually really strange behavior. It's not like the really real velocity location, right? So you have to be really careful when interpreting these plots. But this is basically a statistically stationary flow which has 17 realizations. And we could be doing this all day and always getting different, unique plots of the turbulent flow near the wall. And so that's really troubling, because you would say, well, how do I predict this, like, efficiently? And that's really hard to do. The only way to really do this might be with direct numerical simulation, and then you're stuck using computers, supercomputers all the time, and they're limited by Reynolds number and power. So high Reynolds number of fully turbulent flows still can't be resolved with just computers. So you might say, well, there's some problems with this. And we might note that there's just a large scatter of the data. We do note that, and also remember y is distance from the wall. So these are just like one of many visualizations or measurements of turbulence and its deterministic chaotic nature. And it poses a lot of problems. So how do we predict these flows in a way that can be consistent and useful for the design of devices, for example? And then I note figure 1.3a and 1.3b here. And just so you know, my notes are staggered from yours, unfortunately, because of the way my LaTeX package is not working. Here's 1.3a and b. So what we've done here is we've taken, or Cebeci-Smith, in their experiment, they actually worked for a airframer, which is an aerospace company that makes planes. They've taken all these and just collapsed them on one plot. So let's take these 17 hydrogen bubble profiles and put them there from the CS article, 1974, in one plot, and they just basically put them on the origin. So this is just actually some distance downstream, x, on a fully turbulent boundary layer flow, and all these lines are the hydrogen bubble plots. And no matter how many experiments I do, it's extremely unlikely, not impossible, but extremely unlikely if I sat there the rest of my life with my grad student or whatever, just or technician at NASA, and just take more and more measurements, they'll never be the same, because there are so many different solutions for the turbulent flow. Now, if I take the average of all those, I'll get the solution on the right, which is the average profile. And that looks like something nice that I might be able to predict, and that's true. That's exactly what we might be able to predict in CFD. So this is like the early lesson that is often shown to people traditionally entering the field, where you say, hey, I may have different realizations of the flow, but only the statistics are predictable. And there's also the famous, like, just question you might ask yourself, that if I go down in my lab and say I have a turbulent jet, and I run that jet, and if I can measure the velocity field at all time, at all spatial locations, and I can know everything about the lab I possibly can, is it possible to set up a computational fluid dynamics experiment where I can reproduce that velocity field exactly? And nobody's ever been able to do that. That's because the flow is so sensitive to the initial and chaotic conditions. So the first homework project, which we'll get to maybe late Thursday or a week from now, we'll be programming the Lorentz set of equations to illustrate the chaotic nature of these flows. Okay. So let's go down here and go down to Reynolds-Averaging. Really? Oh, did I miss it on my page up? So as I mentioned, there's these Reynolds-Averaging techniques, and they're either in integral form. No, that's supposed to be form. Let me erase that. Or summation. And so there's a whole another set of techniques that use integrals, but nobody uses that. I just wanted to note it. And we'll be looking at this summation technique. That's supposed to be summation. And there's basically three types of averaging. I do prefer little hyphens there. And of course, there's the time average. There's a spatial average. And if you want properties of both of those, you would have what? an ensemble average. And these are often discussed in basic fluid mechanics classes sometimes at the graduate level. I'm not sure in this department people get into it, like in Fluids 1 or Fluids 2. No, nobody? Okay. So a time average is just where I take any quantity and average it over time. A spatial average might be where I average any quantity, like density or velocity, over a spatial direction. Like say I want to know the mass in the room, I could just take the average of the density if density varies, right? And then multiply by the volume. That'd be a spatial average at one time. Or if I have an ensemble average, that would be me taking, say, a number of experiments and taking those points and averaging. So for example, say I was having a rocket engine and I started my rocket engine and I measured something in the turbulent flow field, in the exhaust of the flow field. And I would maybe measure the velocity after 10 seconds after the rocket engine starts, or maybe less, maybe 0.01 second. So the flow is not statistically stationary because it's accelerating and developing because the rocket engine's starting. If I took a time average over the start time of a rocket engine, I don't know what that would mean. It'd give me some like intermediate value. And so an ensemble average is probably the most general type where I take a number of averages, say over where a rocket engine is starting, is my favorite example, and I put the probe here, and I would take, say, an average n1, 2, 3, 4, etc., and I would take all these and I would find, say, u bar at time equals 0.001 seconds. And I would do that for the same engine maybe 40 or 50 times to find a startup value. It's an ensemble average. If I took the time average over a flow, which is accelerating like that, it wouldn't be helpful. So Reynolds averaging actually focuses on the first approach, which is time averaging, which you'll see in a second. And down here, I've noted that time averaging is most appropriate for stationary turbulence. And you might say that it's a turbulent flow that, on average, does not vary with time. And maybe you can give me an example. There's lots of examples of turbulent flows which are statistically stationary. So if their time averages are the same today or tomorrow, but at any instant they're always different. So anybody want to share an example? A jet flow. Yeah, so a jet flow, if in the plume in the jet, if it's running like in a rocket engine or a jet engine, my throttle's at the same position, the same value, then the flow would be statistically stationary. Boundary layers, co-ed flows, swirling flows, shear layers, backward-facing steps. These are all statistically stationary, but at every instant of time, they have a different realization of turbulence. So this is very frustrating, because if you're trying to predict turbulence, it's very difficult without taking averages, because that's what's predictable. And so here in equation 1.1, our first equation of a few of this class is a basic time average. So F is really any instantaneous flow variable. That could be the density rho, U, V, W, P, or T. That's densities, velocity components, pressure, or temperature. They would all go in there, and they're functions of space or time. And we would integrate over a large amount of time, capital T, and let T become very large. And we'll note that in practice, in labs, or CFD or computers, we can never really let T go to infinity because we have a finite amount of data. So it's really a very mathematical definition, and it's just nothing but averaging in time, because we go from T to T plus capital T, which is the total time of the average, over dt, and then you'll notice here, capital F sub T would be our spatial average, and we drop in the argument time T. So, that's all well and good, and that gives us a basic average. This is really what Reynolds averaging is all about, and that's why Reynolds averaging is useful for stationary flows. And when you run RANS models on non-stationary flows, people do all the time. They just do an unsteady RANS simulation, and they break a bunch of assumptions. But it turns out that those simulations are often very good. Like examples of non-stationary flows might be the atmosphere. So a lot of RANS models were applied to atmospheric flows to predict weather and hurricanes and whatever. But it turns out that they're not as good as, say, unsteady simulations like large eddy simulation, which is a spatial averaging technique. And we'll talk a little bit about LES in this class. You can also, as I mentioned just before, average over all space. And that's what we get in equation 1.2. And we'll just call that f sub v as an example. And here we have the same functions, right? So we get x and t. And if we average over 3 dimensions in a volume, dv, and let v become large, we would just, in the same type of definition from 1.1, we would get a volumetric average. So that's time and volumetric averages. There's the third average I noted, which is ensemble average. And I wrote this out fully because I think these things are important just for mathematical definitions. If we have n identical experiments with the same initial condition and boundary conditions, and we might differ them by infinitesimal perturbations to get different realizations of turbulence, and we average over n experiments, then we'll get the ensemble average. So you see, this is nice, the ensemble average. It's more general because we have an ensemble average depends on x space and time, unlike the two previous averaging techniques. And we'll say f sub n, where n is our nth experiment. So if you start up your rocket engine and take 20 startups, you might have some idea of what the average thrust is at some amount of time. That's how simple it is. That's the definition of ensemble average. And this is one important definition you might see in turbulence literature and these CFD type classes, and that's the ergodic hypothesis, and that states that for turbulence that is both stationary and homogeneous, we may assume that these 3 averages are all equal, and we might do that sometimes. So stationary turbulence we just defined, and homogeneous means what? That if we look at statistics in a flow field at different spatial positions are always equal. So you say, well, that's weird, because boundary layer turbulence is not the same everywhere. It varies from the wall, and so does jets and shear layers and wakes. So what would be a flow where the statistics are the same everywhere? And I can think of one right away, which is wonderful, and it's called grid turbulence. So say you are in a wind tunnel, and there's a contraction section. Here's your test section. And you might have a grid here, which is a honeycomb grid. And downstream of the honeycomb, that turbulence quickly decays, and maybe 10 length scales of the honeycomb diameter becomes homogenized. And that's how, in practice, a lot of people remove turbulence in these types of tunnels. Okay. I do want to say that now we can define the Reynolds average itself, which I wrote down in the previous class. And we'll say that this is really the velocity. This is the velocity as you know it from the equations of motion, if that's the Euler equations or Navier-Stokes equations. And we do a summation decomposition into an average part, which we'll just write as capital U, okay, and a fluctuating part, which we'll just write again as with a prime. So this is the fluctuating part, and this is the mean. So we can also do that to other variables, right? So we have densities, pressures, temperatures, any unknown variable in any set of equations. It doesn't matter if it's Navier-Stokes, it could be Maxwell's equations or any other PDE. We can always decompose it like this without any loss. But the problem is when you start doing statistics, you might have to introduce some extra assumptions to this process, which could be difficult. And I would like to note that by convention, these instantaneous variables are denoted by the lowercase symbols, and the mean will be uppercase, and the fluctuating part will be lowercase with a prime. So these are the original variables, the mean, fluctuation. I also do a subscript I here for each component of the velocity field, okay? And this in figure 1.4, I think, really illustrates these ideas. So the x-axis here, right, this is time. The y-axis is going to be the velocity. If we set I equals to 1, it might be just u, the u component of the velocity. T is our averaging length, and we might look at a small time scale. We'll just call that T1, and a large time scale we would call T2. And you see this dotted line here. So the actual turbulent flow might be denoted by the solid line, for instance. And the average would be ui, and the prime would be the difference, of course, between ui and capital U sub I. So that's the fluctuation. So all we've done is say we're going to average our flow field and say there's a fluctuation. And that's exactly how we can define now some of these variables. So if you look back at equation 1.1, let's just scroll up there, if I dare. There's our definition of, say, a time average. Let's apply that to an actual fluctuating quantity. And, you know, if I go into like a turbulent flow, like a boundary layer or a jet, and I have a hot wire measurement, I'll get velocity fluctuations just like this. And in compressible flows, they're always going to be continuous because there's any shocks or shear layers or slip lines. And we can define our average velocity like equation 1.5. So just like 1.1, we have our actual velocity fluctuation. We average it where the averaging time is large, and we'll get our mean value u. So we have our average quantity. You might also ask yourself, well, that's nice. Another property we'll need to develop the Rand's equations for turbulence modeling will involve averages of averages. So without even looking at 1.6, if you have a time average of something, you get, say, a value of 20 meters per second, and I take an average of 20 meters per second, what should I get? 20, right. So this is 1.6 is the definition of essentially averages of averages. That if I put in an average and take an average over it, I should get the same thing, which is an important thing to note. So that's just like in here, you notice the average of the fluctuation of the actual velocity is about the fluctuation, and it should be an average of an average. And then there's the question, why do we do that crazy step in 1.6? It's to show you mathematically that if we take the average of a fluctuating velocity or any other quantity in a turbulent flow, which is stationary, statistically stationary, that the fluctuating part should be by definition a zero. So say I'm in the lab and I take a measurement, and it's a turbulence measurement, and it's the velocity. It's stationary, and I've taken a long time average, and I find the mean. If I then find, and if I subtract the mean and velocity, and I take the average of the fluctuating quantity, it should be zero by definition. And that's what you see right here on the right-hand side of 1.7. Okay. So this is okay, but it does depend on needing long time averages in practice. And you might say, well, how long do I need to do a time average for it to be useful? And usually you would say it's over many integral time scales of turbulence or realizations of the flow. Or you could just do kind of a guess and check, but if you're in the lab, that may not be possible. It's expensive to run experiments. So we have to go in there with some kind of idea of how long these averages are going to be. And, oops, put that there. So we can't do t to infinity in practice. That's nice. But it would be nice if we have longer time averages. So let's just talk about a quick example to really illustrate this. I wrote as an example, let's say we have a flow at 10 meters per second in a 5 centimeter diameter pipe. And let's say, from just kind of looking at experiments, you'll need at about an integration time of about 20 seconds. So to arrive at statistically independent values of turbulence statistics. So that means that the flow has moved about 4,000 pipe diameters over to find statistically stationary turbulence statistics. And that's a long time and a lot of flow. And this is a very small tunnel. So the longer your time scales are, you need to multiply them by 30 or 40 at least to arrive at these values to get independent values. Another problem which is often encountered is when you have flows, they may not have this like nice single value of an average. It might be periodic, and you might think of flows where that's the case. So I can think of one right away, and that's a rotorcraft, helicopter blades. The turbulent flow over those might be periodic if you're in forward flight, and the periodicity is going as like the rotational speed of the helicopter, right? So that's really shown right here in figure 1.5. So this is a little bit different than the previous figure. So once again, we have the x-axis of time. Y-axis, we have a velocity fluctuation. Now, here I've introduced two different time scales, which we'll kind of talk to later and define. One might be T1, which is a short time scale, and the other one might be T2, which should be much, much, much larger than the longest period of the flow. And you can see if we do short time T1 averages, you'll get some kind of like slowly varying average in the background. And we still have the fluctuation values about it. So if we define a fluctuating value and a mean value, they should both be consistent as long as you choose the same T1 and T2. But if you don't have a long enough period of collection of the data, then you're going to be above or below the actual long-term mean. And you can see a huge problem with these techniques is that if you have some like low frequency oscillations in your data like this, and you just do a time average, you're never going to capture them. You just find like a mean about it, and that can be really difficult to do. So that's often a slight problem that we have to deal with. So helicopters is a great example. Automobile mufflers, because of course the engine has a cycle. Those are all examples where they become problems. So how do we handle that? Well, we'll try and modify our equations 1.4 and 1.5 to try and handle this. And we'll come up with these new types of definitions. 1.8 is very much the same, but then you see 1.9. We need to like put restrictions on the time. And it should, to be useful in a RANS closure and prediction, it should not be longer than long time scales, and it shouldn't be too small to only capture like little parts of the fluctuations. And so this is a philosophy. And in practice, you might also say, well, how do I know what those are? And you might just say, well, best practice is an experience in a lab, because I have the data and I can look at it and I can choose these time scales. But that's not a very satisfactory thing when you're trying to do prediction of turbulent flows, because of course when you're predicting turbulent flows, you have no idea what the right answer usually is. So this is what is called in the community as the spectral gap problem. And I've introduced it through this example. Okay. So there's a few assumptions for the spectral gap problem to be overcome. And one thing that has to be true is that there has to be a huge difference between the small time scale and the large time scale. And thankfully, in all turbulent flows, there's a cascade, and there's huge differences, sometimes 2, 3, or even 10 or 12 orders of magnitude between the smallest little time scale of turbulence and the biggest. And maybe on Thursday, we'll show this turbulent cascade problem, and I'll show you why Andrei Kolmogorov argued about the turbulent cascade in the Soviet Union, and it's so well adapted today. Really, there's very few engineering flows that satisfy all these conditions. And we'll just say, so what? We're going to do it anyway and see what happens. And it turns out that sometimes even if you violate these statistical assumptions that we're talking about, it won't matter anyway. And these means and their product don't vanish. And we'll see that when we're going to derive the Rand's equations in a few minutes. Now, let's try and look at some properties of averages. And I want to introduce these properties of averages because we're going to use them to take the Navier-Stokes equations and do Reynolds-Averaging to introduce the closure problem. So this is sort of like setting up the major problem of turbulence in the whole field. So here I wrote time averaging processes involving integrals over time, commutes with spatial differentiation. So you see in the Navier-Stokes equations, there's terms like what? Partial p, partial x, there's partial u, partial y, partial v, partial w, etc. These are all spatial differentiation. And here we're using Einstein or index notation. Here. So this little comma I, this just means partial p, partial xi, for instance. And you said I equals 1, that would be x. I equals 2, y. I equals 3, z. And over here, this just means we would differentiate with x then y, if I equals 1 and j equals 2, for instance. Now, the bar means what? That's the averaging property, meaning we're running it through the temporal averaging integral shown earlier. And so this is stating, and you can show there's, this isn't a proof class, but you can show that if you take an average of a spatial derivative, it's just the same, okay? So that's good. It means it's a linear operation. And also, if there's, say, constants, we can pull them out or inside the averages. And that's written down here in 1.11. So for example, if A and B are fluctuating, then the average of C1A plus C2B equals C1A plus C2B. So that's, I could also put bars over here, but that's useless because averages are averages. And you can always do that like with an experiment, just to prove it to yourself. In nature, you can always take your turbulent flow. Hello, got some chairs for us, huh? Okay, you can always take multiply your turbulent flow theory with a constant. I mean, it's no longer a solution of Navier-Stokes equations or anything like that, but you can see that the constant can be pulled out of the property. And that's fine. So, for time averages of unsteady terms, partial u, partial t, that will be 0 for stationary turbulence. So what does that mean? So, of course, an average of a flux, just partial u, partial t itself will be non-zero. But then if we find the average of u, that will be a constant in stationary flow. And so partial capital U, partial t, would be 0 because it's a constant. And then if it's a fluctuating quantity, we wouldn't be able necessarily to say it's 0, but if we average it, it would be 0, right? So we would say partial u prime partial t average. What would that be? Well, something to think about. But let's look at 1.12. And we'll take a time average. And so we have U bar and the fluctuating quantity. So here's the average and fluctuation. We can expand them like this. And what do we find? We see that the second term on the right-hand side of equation 1.12, this one, can be neglected. So here's an assumption, provided ui prime is small relative to ui, the main average. So what does this mean? It means we're assuming that t is very small relative to the time scale of the mean flow. So the mean flow can still vary, but that time is going to be smaller than the variation, and also that t is much less than t2, which we defined earlier. So this has to be true, or else this whole Reynolds averaging technique and reduction won't be possible, and we won't be able to make nice turbulence models. So this is an important assumption which has been always built into every Brandtl model and every CFD code that's ever really been developed, and it works well. But you'll see that sometimes U prime is not small relative to the average at all. It could be 10% or more, and we'll show an example like that in a boundary layer flow in a second. Okay. So with these assumptions, we can write down this equation, that partial fluctuating quantity, partial t, of the velocity will go as the average, and that fluctuating quantity will be small according to this assumption right there. And I wrote right here what I just said verbally. Sorry about that. It's a questionable assumption. And I've given two examples of this. For example, in a free shear flow, you'll see that you have very large turbulent fluctuations relative to the mean quantities, and that's also true for boundary layers, which will show in a plot. But a free shear flow might just be one where you have velocities like in a top hat profile like this, and there's a smaller velocity profile like this, and then there's a shear like this that develops into turbulence. And certainly in these high-speed shear layers, your turbulent fluctuations are huge compared to your mean flow. That's also true in pretty much any boundary layer, turbulent boundary layer very close to the wall. And this is one of the complications, that we cannot assume that these fluctuations are small near the wall at all. And this also means that our time averages for analysis, especially for time marching numerical methods for solving steady flow problems, might encounter some major problems, because the unsteady terms we're calculating in unsteady RANs are nothing like fluctuations at all. We're just really getting the average quantities. The average quantities are changing. The statistical quantities the fluctuating quantity we never really know from a RAND solution. You'd have to do a totally different technique. So you're really only getting in an unsteady RAND solution the variation of the average values, which I just erased. Just write U bar. How's that? Okay. As you noted, this equation up here depends on that questionable assumption, and I'll show in a few slides here, and I might direct yourself to a figure later, which we'll talk about, and it would be figure 1.6, which is on page 23 of my notes, but it's many pages later, and you see in that figure the averages of the fluctuating quantities are much larger than 10% in the mean flow values. So those are just some properties of averages that we're going to have to use. And we'll look at those and use those when we derive RANs. So I think, let's see here. So the first class, maybe this one goes for another 5 minutes. So I want to talk about correlations, and then we'll take a few minutes break. And then after the break, we'll derive the Reynolds averaged equations. So let's look at this correlations. So we've already talked about like 1-point statistics, right? Just taking time average, spatial average, ensemble average, how those averages work on particular quantities. And we talked about some of the assumptions we've had to make to be able to develop these in like world famous equations, which pretty much everything's designed by. But it also depends on correlations. And you might say, well, if I have two different quantities, like a fluctuating density and velocity, how are they related in space and time? And this is the whole area of correlations. And we're going to talk about 1-point correlation, 2-point correlations, 2-point cross correlations, and all these are going to be important for turbulence modeling. So I've already mentioned we looked at averages of linear quantities, but then I asked the question, what happens when we average the product of two properties, say phi and psi? And you could just imagine those are two flow quantities. It could be any two. You could do two velocity components. You could do a velocity component and pressure. For example, that would be, say, U and P. And ask yourself, how are they correlated? And so high correlations in words means that they're highly related physically in some way. And if they're uncorrelated, then they have nothing to do with each other. And it's just a mathematical operation. And it's defined by simply the average of the product of the two quantities. I've written that down here mathematically in 1.14, excuse me. And so what we'll do is to take phi and psi and expand them into their mean and fluctuating part. And then we expand inside the average. And so we'll get the means, the mean times the fluctuation, the mean times the fluctuation, plus two fluctuations. And it turns out that a mean quantity multiplied by its fluctuating quantity and average will be 0. So this is 0, and this is 0, and we find this definition. So you can might as well just write phi psi bar equals phi psi plus phi prime psi prime bar. And that's nice. Oh, I'm sorry, Mr. Barr. Okay. So what does this really tell us? It tells us that the mean value of a product like phi psi bar differs by the product of the mean values. Of course, this doesn't just apply to turbulence, it applies to any stationary statistical process. And you can say that phi and psi prime, if they're 0, that implies that they're uncorrelated. And if they're not equal to 0, then they have some correlation. And this probably goes back to the famous saying I often see people say that correlation doesn't imply causation. So just because two things are correlated doesn't mean one caused another. And that's seen a lot in our society. For example, people might say, well, maybe someone can think of an example. Let's see, clouds cause rain, but that might have some correlation, but I don't know if clouds themselves cause rain. That's not like the cause of rain. Another one might be, I'm alive, so I'm breathing, or I'm breathing, so I'm alive. Is one causing the other? Is there a correlation between it? Certainly there's correlation between it, but one probably didn't necessarily cause the other. So you can apply correlations, but it doesn't mean or apply cause and effect. And maybe it's good to give fluid dynamic examples because we're in a aerospace type class. And you might say, well, the stagnation pressure of the jet flow has increased as I increase nozzle pressure ratio. So there's a case where there's high correlation and causation. Or you might say the speed of the jet has changed because I've changed nozzle pressure ratio, and that wouldn't be, that is correlated, but it's not causation because that's also controlled by temperature. So there's examples where you have to be really careful. You might find high correlations, but it doesn't imply cause and effect. And you might see that a lot in our society. Anyway, one other thing, and you might say, why the heck am I doing this? There's the triple product. So what if I want to say, okay, well, if I can do two things under the average for a correlation, why not look at three? And that's called the triple product. I don't know if anybody ever called it a triple correlation. But here we are. We have phi, psi, and I'm forgetting my Greek variables today, and we're going through COVID, so we should have all learned them all. I'll just say psi. And we can apply the same properties. So what we do is we put in, say, phi plus phi prime, psi plus psi prime, and what? Psi plus psi prime, and over bar. Then I expand them out, and anywhere I have the product, like two averages are an average times a fluctuation, averaged would be 0. And I throw away all those terms, just like I did in 1.14, and I find this equation. And why do I care? Because when I do Reynolds averaging, after our, I guess, a small 10-minute break, you'll see that we get triple correlations. And it's going to be horrible. But that's what Osborne-Reynolds decided to do.